The line to the slice inside the pyramid is solved in terms of aperture of the eye, estimated tilt of the slice at the x and y axes, distance d to the center from your starting point A. That's the good news. The slice represents an arbitrary element in the periodic table of elements from chemistry. Different orientations of that slice represent different elements. It's a guess that this compares to the chemistry phase diagram, where the area inside the pyramid, above and below the cross-section, represent different phases, solid, liquid, and gas, that the element can possibly experience. The thickness of the cross-section is its stability at the ambient phase. As you look through a microscope or as you traverse along an orbit using a telescope, the grid lines point to the center of the object for reference. What we're really inspecting in this illustration is a small arc of a whole circle rotated about the center. When you observe an XY graph, what is most typical when learning mathematics, you are looking flat at four quadrants: positive x with positive y, negative x with positive y, negative x with negative y, and positive x with negative y, respectively. Technically, there are 8 quadrants because all of those can sit into the page as well as out of the page. So there's 8 blocks in the shape of a cube. Recall the enclosed chemical illustration. The individual slice dips below the axis as you rotate the pyramid about the corner. Half of the slice during rotation falls into the page, into the negative z. We don't have to concern ourselves with this at this point, because geometry draws it, and so does the math. So let's give ourselves a break and stay in the positive x, positive y, positive z quadrant. A special sliver within that quadrant is pictured. As you focus on the center through the microscope with your right eye, the coordinates line up with that center along a distance d. At the same time, you're also viewing both sides of the slice. That's 3 points of reference in a single snapshot from point A. Your left eye is doing the same thing, lining up with the eyepiece, looking straight down at the center, and also at the same 2 sides of the slice. That's point B. Notice in a microscope that the 2 eyepieces point straight down in 2 different trajectories to arrive at the same point in the slide. This is done by using mirrors within the scope. So the angle between them is known as a function of distance to the center of the microscope slide. Or in the most general case, the central black hole of a galaxy. Here, distance isn't known, but the reference tilts at the x and y axis can be estimated. The equation is left in variable form because at different scales, the pieces of information we can be sure about are different. Galaxies are slow moving, while up-close smells are given off and travel very quickly.
Galaxies matter because they represent a portion of nature that moves slowly enough to observe structure in the emission spectrum. Electrons bounding around an atom are too jostle to regard, but a galaxy maintains the same pattern over long periods of time. Before we rush to throw out supermassive black holes, consider the predicament. Look at the illustration and reduce the slice to near zero. Look at all the lines that have to be perfectly described in order to even understand a black hole, each totally unique yet reducing to nearly the same line as they draw closer and closer to the central point. And this drawing is exaggerated to show that the lines are different. In distant black holes, points A and B are so close to each other, parallax angles, for example the slower changes in a distant forest as you drive quickly down the road, described as parallax, were completely abandoned pretty much as soon as people started looking up. Astrophysicists explain a radius just outside the black hole as a point when things start making sense to them. Let's for a moment gloss over the fact that this pinpoint, at great distance away, is itself thousands of light years thick. It is no surprise that astronomers described the confusion as best they could, even wrongly, because the alternative is to say that we have no idea what goes on in a black hole. Relax, it's covered here in the material.
We know enough from the illustration to see that there are multiple points of interest along the same line of sight, blocking each other from a solid view. There's the point on the slice as well as the point behind that on the XY plane, conveniently staged at 90 degrees to your initial view at point A. This reference plane is there to identify the tilt axes of the slice. The XY plane is for A only and doesn't line up at 90 degrees from point B, which is the next issue to discuss. For now, we can be happy that the diagram is enclosed, meaning there are no lines veering off the page. Every line drawn has two endpoints, and each point is connected to another line, completely enclosed within the page. That's an important distinction, because it means that the geometry is manageable, meaning that all unknowns can be described in terms of the rest. So what are we contemplating? The goal is to describe the slice from 2 points, A and B. The logical scenario is to ask where they meet, and the answer is along the line of sight for both of them. That's the point of interest, the target, the object of preposition, and the thing we know the least about. After all, the point is moving, and the size of the cut observed inside the pyramid is dependent on how close that point is to your eyes, A or B. As the point gets closer to the eye, the area of the cross-section looks bigger. The pyramid grows. If you cross your eyes, the two images or edges that you have to compare grow further apart. If you look at a star in the distance, very small differences between the eyes need to be observed to get a reading, because the slice is so small. So as we compare the variety of shapes formed by this illustration, we gain knowledge about individual angles and individual lines one by one in terms of the knowns, until we finally describe the line of sight to the object, be it a fungus on a petri dish or a star on the outskirts of a distant galaxy.
What happens on a line is equal to what is received along that line. Our perception of what is received is an accumulation of the events along the line leading up to the observation. Most integration of a curved line is done by taking derivatives at each turning point. So when a squiggly line goes from turning up to turning down, the inflection point is found by taking a second derivative. Engineering is so obsessed with derivatives, trying to describe faster and faster turns, they didn't learn a slightly different way to perform integration. Line integration uses an arbitrary observation point and draws a straight line to the squiggly one. Another straight line is drawn for each tiny segment of the squiggly line, which also adds up to describing the curve. This is done without taking a single derivative, which is good because finding the derivative is not always easy. In the case where there's so many turning points in the emission spectrum received, line integration is really the only way. So the line integral of the structure, a geometric combination of mass and charge enclosed, is the same as the line integral that's received by that structure, as it is received in a duration of time. We would effectively integrate a line that couldn't be integrated with an equation that is the lowest derivative possible.
Engineering is far ahead with the advancements of flying drones and hybrid cars, but flying saucers are right around the corner. Chemistry is far ahead with the advancements of physical chemistry from quantum mechanics, and we know most of the impactful reactions between elements in the periodic table, at least that energy is transferred from before to after. But what happens during the reactions is still a mystery. Biology is far ahead on how to keep a human body healthy, but safe medications still elude us. In my opinion, pretty good is not yet great. The choice is ours to attempt the geometric challenge. Here's the door.